Alright team, so I promised a video since we're not meeting today. And then this is probably more helpful than if I told you in person, because you can keep replaying it if you feel like you didn't catch something. Alright, so right now I'm going to go over the amplifier, the feedback, and the oscillator. This is from the Troyk paper. I believe I shared it with you guys. So let's go over it. Before I started this video, I did label some of the parts of the circuit. So let me explain some of them. So and then we'll go kind of step by step to see how this works. And you're gonna basically do the same thing. I think the only thing that has changed is like the voltages that you're applying. Instead of 5, I think some of them are like 3.2 or something. So let's go through it together. So where do we start? So remember that the goal is to have basically a transmitter and a receiver, which are not physically connected to each other. They're separated by a distance, and your job basically is to provide power to the transmitter, and the power has to be AC, and then that way that the magnetic field that you create is an AC magnetic field, which can get captured by the receiver. So you can't just put a function generator and attach it to the transmitter, because the transmitter, the amount of current that you need to produce like a useful magnetic field has to be really large. And I think that, I'm sure of this, that the function generator can only produce up to, I think, like 50 milliamps of current. Maybe a little more, but you definitely need way more than that. You need more like in the amp range. So what you have to do is, instead of just attaching the transmitter coil to like a function generator or an oscillator, you have to actually have an amplifier, so that you can provide a big enough current so that you produce a big enough magnetic field. Alright, so let's talk about the amplifier first. So I think I've already gone over this, but let's go over it again. So the way it works is you basically have a power MOSFET that's shown right here. It can be NPN or PNP. It doesn't really matter. So what you're going to do is you're going to attach that, and then you're going to have a parallel capacitor here. I believe these values were determined by the previous group, so just take a look at what values they used. There was a little bit of tweaking, but they shouldn't have changed that much from what we have. Well, they will change because the inductor is different, will be different. Okay, so once you calculate that, which we'll go over in a separate video or separate meeting, but as of right now, just use whatever they have used. And so let's talk about what this does. So you're going to put a parallel capacitor across the MOSFET, and you're going to then put this inductor coil from a positive 5 volts to the top of that capacitor. And so the point of this, it's called L1, is to basically provide constant current. So you're going to be switching this thing on and off, and there's going to be a lot of like pulsating voltages and currents going through here. But you're going to want to constantly basically provide current to this whole circuit here. So what I'm basically saying is, or a different way of saying that, is that you don't want whatever's going on here to affect what's coming out of the power supply that you're attaching at this point. So to do that, you would just attach a relatively large inductor here, and what that does is it basically dampens out any oscillations that are happening at this like line here, and then that just allows current to just come in continuously through this whole circuit here. So that's the point of that. I think they kept it at 30 microhenries. I think the point here is that this has to be typically a little larger than whatever L2 is, and we'll get to what L2 is right now. So you attach this capacitor, and then you're going to attach another capacitor on this branch here. And what you're going to do is you're going to have then your transmitter. So in this circuit here, your transmitter is represented by L2. So your transmitter is just an inductor. The value of that inductance is going to depend on the design of the transmitter, and that's going to be, I believe, Fatima's job. So once she finalizes this transmitter um, inductance, we can just assume that she's going to use the same transmitter as the previous group, but she'll obviously make a new one, and it'll probably be around the same value, so we don't have to redesign this whole thing. So once you get that value, then you can calculate C2 and C1. So let me explain exactly how this thing works. So this circuit works as basically a resonator. So you're gonna have to probably go to like your EC240 or equivalent kind of class to remember what that is. But this MOSFET, what it's really doing is it's not acting like an amplifier as you've seen like maybe in EC340 or 440. What you're using it as a switch. So this signal right here on this line, that's basically going to be a from 0 to whatever the saturation voltage is on the base of this thing. I'm sorry, the gate. Sorry, I'm getting my transistors confused. So you're gonna apply that on this line. So you're gonna have to look at the data sheet to see what that saturation voltage is. But I think I mentioned to you that it's like if you do 10, that's fine. I don't think 5 turns it on completely. So let's say you put a 5-volt voltage here. That's gonna turn this on, which is gonna short this thing. Okay. What that does is that causes current to come this way, and it's gonna go all the way to the short back to ground. Once you turn it off, this becomes open, and that current then gets diverted to the capacitor, so charging it. So you're going to have an increase in voltage here, and you're also going to have current going down this leg right here. Now if you notice, if you remember from 240, when you have an inductor and a capacitor in series, or even if you have a capacitor and inductor in parallel, that there's going to be a specific frequency at which those two elements are going to be basically communicating energy back and forth to each other. So like in this case, if you're switching this on and off at the right frequency, then these two are going to basically resonate. And what that means is they're going to produce a voltage across like the inductor that is large, even if you're not putting that much current in. So that's like kind of like what makes this an amplifier. It's not so much that you're using the MOSFET to amplify, it's that you're using the switching the on and off and the frequency that you're switching on and off that causes this to basically produce a large voltage and a large magnetic field. So when this is basically off and this is open, then current goes this way and this way. So you have an increase in voltage at this node, and you have current going through here, which is building up a magnetic field this way, right? So you have current going from right to left in this case. When that happens, that produces a magnetic field, and then when you switch it up, when you switch it on, that current gets diverted back to this node to go back to ground. And so you have like the current going back from right to left and left to right, back, forth, and that is what's going to cause basically a magnetic field to basically change direction from up, down, up, down, up, down, which is basically going to be transmitted to the receiver. Okay, and you're going to get an amplification just by the value of C2 that you pick and the L2 value that you are left with. Okay, so what is this thing right here? Alright, so once you get a hold of what the amplifier is basically doing, then let's talk about making it more efficient. So I told the last group this, but I think the first 2 groups just did this amplifier and then they just tested and that's it. So it turns out that this transmitter is communicating with another transmitter that I haven't drawn up here. So let me draw that. Sorry for the weird noises. It's cardboard. All right. So I'm gonna try to draw. Let's see if I can draw. There's gonna be. That's supposed to be an inductor. That's going to be the receiver, and so they're communicating with each other. Okay, so because of that, this inductance value is going to change because of mutual inductance. I don't know what class you might have learned that in, but I guess you're learning it now. So when this receiver gets close enough to the inductor, it's going to interact with this L2. And what that's going to do is it's effectively going to add or subtract depending on how they're coupled or interacting, and change the effective inductance of this thing. So why is that important? Because this amplifier is not a static thing. So like if my receiver is perfectly aligned with the transmitter, you can then say, okay, my effective inductance of that whole system is, some number, and then you can design your amplifier around operating at that point. The problem is that sometimes things move, especially in humans. If you implant this thing, it might even move like not even like a millimeter, half a millimeter. That does affect the inductance, and that's going to affect this finely tuned like circuit. So what you have to basically do is be able to effectively sense that change in case like the receiver moves or the transmitter moves. You have to have like some feedback to correct any misalignment. So that's what this bottom part here is. So this little donut looking thing, that is a toroid. That's basically another inductor. But notice that it's not actually like in line with the wire and the amplifier. What it's really showing you is that you have like this donut with wires wound around it. It's called a toroid. And you have a wire going through the donut hole. Alright, so what does that do? So it's kind of like with the transmitter. So when current comes this way down this line, and then goes back, when you have the switching, you're going to have current back, forth, going, into back, back into the hole, back out of the hole. And that creates a change in current, which we know from Faraday's law will produce a voltage, because you can sense it now because this is an inductor. And that will produce a voltage across these two lines here. Alright, just to reiterate, this is not in line with this wire that's in the amplifier. It's like, imagine like you put a ring around a wire. And so this is just sensing the current direction change in this section of the wire. That produces the voltage across these two wires, and that comes down here. Alright, so now that we've talked about the amplifier, let's talk about the zero cross detector. So the way this works is that it's supposed to sense, okay, even if you have a change in the inductance of this thing, that will obviously change how fast the current's going through this donut hole. And so you can sense that with this specific device, and then feed it back, and then just basically what's going on down here is this is basically going to effectively tell the switch when to turn on and off, so that you can basically turn on and off according to whatever the change in the inductance is up here. Alright, so this is going to sense whenever, and there's, this paper kind of talks about that, but what this does is it senses, okay, when is the current crossing zero? So when or voltage, whenever I have a voltage going this way, let's say that we're doing the right hand rule, that will create a positive voltage. And then when it reverses, that's going to create a negative voltage. And at some point in that transition, it's going to have to cross zero. And so that's what this is basically detecting. So once you have this voltage across here, what you're going to do is you're going to apply these diodes. And the purpose of diode 1 and diode 2 are basically to clamp the amount of voltage difference across the wire. Because your comparator that you're going to use is sensitive to how much voltage you can have across it. So if you have too much voltage across these two wires, that can burn out the comparator. So what D1 and D2 do is they basically clamp the positive voltage and the negative voltage. So if you remember from 340, like the diodes will have a voltage drop of like around 0.7. So what that's saying is that this line up here is not going to go above 0.7 volts. And this line down here will not go above negative 0.7 volts. And that's a good thing, because remember that you're only detecting when it crosses zero. You don't care how big the voltage is across here. So this will clamp it, so that you're not burning this thing out. Okay, that gets fed through here, and then this is basically a comparator. So what this is doing is it's going to say, okay, well, I'm going to compare the positive, the non-inverting terminal with the inverting terminal, and whenever this wire right here is larger than the negative wire, this comparator will produce a high voltage at the output. So it'll produce like a 5 if you're powering it with 5 volts. whenever this voltage at the non-inverting is smaller than the inverting, then it's gonna then produce a zero. It won't switch on. So that's kind of how this goes. And so this is basically just telling you, okay, when am I ever crossing zero at this point? And so the zero, this is not shown here, but we actually grounded in our circuit. So this bottom here is grounded. Actually, is it grounded? I have to double check that. But that's how you know when basically you have crossed that threshold. I have to double check if this is I believe it is. But I'll make sure. Okay, so once switching on and off, this goes this way. Okay, this C3 is just a decoupling capacitor, so this is just basically like filtering out any DC voltages that are present in this signal here, which can happen. So this makes it an AC signal, and this is just a typical relaxation oscillator. It's like positive feedback, and what's important for this circuit here is what's down here, C4 and R8. So these two, it's basically an RC circuit. These two will essentially determine the time constant of the voltage that's sitting right here. So when this thing turns on, that'll charge this capacitor, and it'll charge it to some value, which typically is going to be whatever you're powering this comparator at. And how fast it gets to that point is determined by C4 and R8. And what you're going to get is you're going to get kind of like a, let me draw it out. You're going to get, let me put it in green. You're going to get a thing that looks kind of like that, where like how much this goes up is determined by tau, and tau is equal to RC. Sorry, I'm drawing with the mouse. It's like horrible. Now my microphone fell. Okay, whatever. All right, so that's the relaxed oscillator. The value up here should be 5. All these things will some things will change, like some of the values I tell you, but most of it is true when you're working on the actual circuit. It's just that you have to like tweak some things here and there. So you might not get 5. You're gonna get a lot lower than that. You'll see. But regardless, you're gonna get this waveform. You're gonna get that here, and this is where it gets a little complicated. So let me slow down a little bit. So once you get here, this is just telling you when you're crossing zero. This is telling it when to start. So this is going to be actually driving the actual MOSFET over here. Now, this is going to be basically going from 0 to some value. And then that gets fed through this comparator here. It's another comparator. And what it's doing is, again, it's comparing the signal here, which is this one right here, this little sawtooth looking thing. Not sawtooth, but like this RC looking signal. And it's going to compare it to whatever value this is. Okay, so what is this value here? Now this is where you can set the duty cycle of this specific thing. So we haven't talked about duty cycle, but we were assuming that like you're on half the time, off half the time. And so what this allows you to do is this comparator allows you to basically say, okay, well, I want maybe 20% duty cycle. Maybe I don't want 50, or I want 80% duty cycle. So what this does is it allows you to pick what voltage this is to compare it with whatever this voltage is here, which is this green line here. And you can then turn on and off accordingly. So this line right here, just so ignore this. Let me draw that. I'm gonna just cross this whole thing out. This part right here, we're not doing that. So take that out. We're only gonna do this part of it. All right. So this is basically a voltage divider. And if you notice, R13 is 12K. It's kind of hard to see. R1 and R12 are 10K and 2.4. So this is about, like, if you combine these, this is about 12.4, which compared to 12 is about the same, right? So right now, the way it stands, the voltage which you're measuring here really is going to be half of 5 volts. So you're going to have 2.5 volts sitting right here. And assuming that this is 5 volts where this goes up, you can change this and say, okay, well, this comparator will turn on whenever this line is above 2.5 volts. So once this goes above 2.5, this thing switches on, and then something will happen. We'll get to that later. Whenever this voltage here is below 2.5, nothing will happen out here. So this is basically, again, switching from 0 to 5, and nothing is happening at this point. Okay, you can change this value. So like, let's say that you make R12, so this is going to be a potentiometer, so you can change it. So let's say that you go down to, I don't know, like 1K. That means that the majority of your voltage will be dropped across R13. So because of that, maybe this will be like closer to 4 volts. Let's just make that up. I haven't calculated in my head, but let's say that this is closer to 5 volts, right? That means that when you're comparing this basically has to go up higher, the green, and then once it hits a voltage that's higher than whatever you're measuring down here, you can then this will then switch up, and then something will happen. So this allows you to basically just change what you're comparing the green line to in this case. Okay, we're almost done. So once you compare, then you're gonna drive this BJT, which you have in the lab as well. And whenever this is on, this is gonna basically short it, and this then just becomes a voltage divider, right? And then you're gonna have 2.5 volts here. So again, this is basically this comparing right here is dictating when you're turning on and off this BJT. And so, like, if back to the example of when R12 is much lower and this is closer to 5, then you're only gonna turn this on whenever, for like very short amount of time, right? Because the majority of the time this is gonna be turned off, because the majority of the time this green line is not gonna be close to 5, only for a small portion of it. So you're gonna have, in that case, a smaller duty cycle. If you make this bigger, you're gonna have something that can be higher. So you can, again, change this value here to change the duty cycle, and so this just tells it when to end the signal. So this comparator compares the voltage where you're getting from this little current transformer back from the amplifier. That's when you start your pulse, and when you end it, it's gonna be whenever this is high. And when that's high, you say, okay, well, this is gonna be higher than this one, so you turn this off, and then it's gonna switch it on and off. So basically, it's gonna be a square wave coming out of here, and the duty cycle is gonna be dependent on whenever this pulse signal is bigger than this one right here. Okay, so now, like, let me kind of back up a little bit. So you can see it, because everything's interconnected, how, you know, maybe it sounds a little easy to understand. I don't know if I explained it well enough, but you can tell where it's gonna get complicated, right? I've been saying that out of the comparators, you're gonna get, 0 to 5 volts coming out. That's not true for some reason. Maybe it's the way we're connecting it. What's coming out is a very small signal. I think it's on the order of like 600 millivolts, so 0.6 volts. That obviously is bad, especially when you get down to here. So you're gonna have to change some of these values so that when you're comparing to 0.6 and not 5 volts. The same thing up here. So at every comparing stage, you're gonna get 0.6 and not 5 volts. Again, I'm not really sure why that's happening, but it is nonetheless. So you're gonna have to just basically change some of the values of those voltages and these resistors to match up what you're doing. It still works. It's just that you have to then amplify. And so that's why I mentioned to you before, what's not shown here is a non-inverting amplifier. It turns out that, again, because at this point what's coming out is not 5 volts, it's like a much smaller value, like 0.6, that's not enough to turn on and off this switch here. So you're going to have to add up an amplifier in this case so that the signal that's going to your gate is going to be big enough to open and close it. Okay, so that's all I have. Hopefully that was a little helpful. You can rewatch it and laugh at all my weird noises that I'm making. So that squeaky sound is just my mouse on the little mouse pad. So sorry about that weird noise. So yeah, hopefully this helps. I will try to make another video for the motor controller right after this one, but it might require me to kind of read the data sheet a little more. But okay, hopefully this helps, and if you have questions, let me know. And that's all.